Okay, so let's jump into the wave theory.
In the next 800 years, engineering passed from an art into a science, and the achievements and failures of engineers became truly breathtaking. When the Tacoma Narrows Bridge in Washington State opened in 1940, it was thought to be lovely and elegant in the new lightweight style, but nothing very groundbreaking.
It was a wonderful bridge just to look at. It was beautiful.
The spectacular Golden Gate Bridge in San Francisco had opened 3 years before, with a span almost 2,000 feet longer. On the other coast, New York's George Washington Bridge, built in 1933, was 700 feet longer. But the Tacoma Narrows Bridge would make a lasting name for itself. Within days of its opening, it began to sway like a hammock in the breeze. Pretty soon, it was the most famous bridge in America.
We learned that about the bridge, that when the wind was up, it would become galloping gurdy, move up and down. And when the wind was really bad, we used to ride our bikes out there, park on a hill beside the bridge, and watch it go up and down, just for a lark. They let people go when the dropping was so sudden that it felt like an old-fashioned elevator. Boom, like that.
Galloping Gertie remained open to traffic for 4 months, but in November, everybody was ordered off as a 40-mile-an-hour gale whipped across her deck, lifting the roadway like a sail.
We went out to watch it whip, and it was really whipping, and there was one car on it. But then it got late, and so we left.
By afternoon, the stresses were too much. Incredibly, the 11,000-ton center span ripped away and crashed into the sea. Aerodynamic problems had never been considered important.
All right, so here's a question. Why did the bridge collapse? And you guys are thinking, because it was vibrating too much? What caused the vibrations?
Before.
All right, so why did the bridge collapse? The short answer is because it resonated. Okay, so the next question is, what's resonance? What caused the bridge to collapse is known as resonance. The question is, what is resonance? Speaking of resonance, the term resonance is something that you hear quite often. If you're resonating with somebody's feelings, which means that you're feeling what they're feeling, you're empathizing. That's what it means. If you're resonating with somebody's thoughts, you're agreeing with their thoughts. All right, so when you resonate with somebody's feelings, people usually get emotional. And when you resonate with other people's thoughts, they kind of like you better because you're in agreement with their thoughts. But when there's resonance, if a building resonates, it goes down. If a bridge resonates, it's going to go down as well. So what's resonance? And why did this bridge collapse because of resonance? So those are the things that we will get to discuss.
This one over here is dead. This one over here is alive. Dead. Actually, it's not quite dead. If you get up close to it, you can't hear a ring. Some of them are too subtle. This one, that's not very subtle.
All right, so all these rocks are identical. They look identical, they're identical. Some of the rocks will ring and most of them won't. So what's the difference between ringing rocks and the rocks that don't ring? All right, so which means that structurally they're going to be the same. And you were thinking, oh, maybe some of them are hollow. Oh, that's one thought. And some of you guys will say they have different densities. Okay, so that's a different thought. But what's the actual reason? Okay, so we're talking about waves, we're talking about vibrations. So what is a wave? The definition of a wave is a traveling disturbance that's going to carry energy with it. And the disturbance that carries energy is known as a wave. All right, so when you see a wave, you recognize about what does it do? What it does, it's a disturbance that's going to carry energy with it. All right, so the example of a wave is this. Will this be, can we consider this as a wave? Of course, number one, it's a traveling disturbance. And you know it carries energy with it because it's able to apply a force on its surrounding. It's able to make the other stuff move in the direction of motion, right? So that's a wave.
Yes, it works.
All right, not only is this a good example of a wave, but also explains why blockbusters went out of business. All right, so pick out the best answer. All right, so the definition of a wave is it's a traveling disturbance that carries energy, right? That's your wave. So B is the best answer for that one. In terms of waves, there are two kinds that we'll be focusing on. The most obvious one is called a transverse wave. It's a wiggling. It goes up and down. Right there. All right, so it just wiggles through space and time. So if you end up getting a wiggler, this is known as a transverse wave. The thing about the transverse wave is just take a look at the point of vibration. All right, the wave is traveling from left to right. So this denotes the direction of the motion of the wave. Point of disturbance that you're looking at is going to go up and down. So point of disturbance is going to move perpendicular to the motion of the wave. It's going to be normal, perpendicular to the motion of the wave. So that's a transverse wave. Any wave that does this, any wave that just wiggles up and down, is known as a transverse wave. So the point of disturbance is going to move 90 degrees to the motion itself. All right, so the transverse waves, the examples you're looking at, slinky, it could be a rope. It could be an electromagnetic wave. So those are transverse waves. And then you got the longitudinal waves. These are known as compression waves. So you got the point of disturbance right there. The point of disturbance is going to move parallel to the motion of the wave. All right, so notice that the point of disturbance is just going to pop forward and backward. So the motion of the wave is from left to right, and the point of disturbance moves parallel to it. So that's your longitudinal wave. That's the compression wave. So you have a compression wave. Example of a compression wave is a sound wave is a compression wave. So we've got the compression waves, we've got the longitudinal waves. The thing all waves have in common is they can interfere with each other. So which means that it's going to cause interference patterns. Waves can interfere constructively. So notice that the amplitude is going to get larger. So this is known as a constructive interference. So whenever the waves overlap, what happens is the amplitude gets larger. So that's your constructive interference. And then we can have destructive interference. You got these inverted waves overlapping. And then what happens is the amplitude will diminish or cancel. This is known as destructive interference. So waves can constructively as well as destructively interfere. When the interference is constructive, the amplitude is maximized. And when it's destructive, the amplitude usually is minimized or it simply cancels. It just vanishes. We're going to focus on periodic waves. Periodic wave is a repeating wave, the wave that repeats itself. All right, so the repeating waves are known as periodic waves. They'll either look like sine waves or cosine waves. This is a periodic wave. It's going to maintain a simple shape. It's going up and down. It's undulating. These waves will have common characteristics. They will have a wavelength. That's going to be the size of a single cycle. So here's your one cycle. Here's your second cycle. They will have an amplitude. The amplitude is the height of a wave, or it's the maximum distance with respect to the undisturbed position, which is right in the middle. All right, so the amplitude is going to represent the height of a wave, or its maximum displacement with respect to its undisturbed position. Wavelength is going to be the length of a single cycle. All right, so we will get to use the Greek letter lambda. For lambda stands for L, Greek letter L. We're going to deal with period. The period is the time for a single cycle to form. All right, so here's your one single cycle. You start here, go up, reverse direction, come back down, and go back up the same point. That's the single cycle. So the period is time for a single cycle to form, time for a single wavelength to form, in essence. And then we got the expression for frequency. It's the number of cycles per second. Here's one single cycle, here's the second cycle, third cycle, the fourth cycle. All right, so number of cycles per second. If this is a 1 second time period, we got 4 cycles within that time period. So it's number of cycles per second. The proper unit is going to be expressed in terms of Hz. Hz stands for hertz, cycles per second. It's going to be a reciprocal of the period. Capital T means the period. All right, in terms of mathematics, so let's go back. Here's your one single cycle. Here's your second cycle, the third cycle. All right, so 1 cycle, 2 cycles, 3 cycles. That's what we got. All right, so the time it takes for a single cycle to form is going to be your period. All right, the length of a single cycle is known as your wavelength. Lambda is going to be your wavelength, so that stands for L. The time for a single cycle to form is your period. As time for a single wavelength to form is your period. It's the same thing. A is going to represent the amplitude. That's the maximum disturbance that a wave will undergo from its undisturbed position. A is going to be expressed in terms of meters, amplitude. Greek letter L, lambda, is going to be our wavelength. Proper unit is going to be meters. T represents the period, the time for a single cycle to form, expressed in terms of seconds. And then we got number of cycles per second. Is known as frequency. All right, so it's a reciprocal of a period, the number of cycles per second. The cycles per second, or Hz, hertz, are the units that we get to use for them. All right, so this wave is going to have a speed. This wave is traveling from left to right. It's traveling in this direction. It's going to be moving at a given speed. All right, so its v is the speed of this wave, or wave speed. It's going to be expressed in terms of meters per second. It's going to be the product of the wavelength and its frequency. All right, so the wavelength times frequency is going to give us the wave speed. All right, so the wave speed is going to be a product of wavelength and frequency. That's the way we express it. All right, so the wave speed is going to be constant. So the question is, if the wave speed is constant, for a constant wave speed, frequency and the wavelength will be inversely related. All right, so if you reduce the frequency, the wavelength is going to go up. If you increase the frequency, the wavelength is going to go down. So we got this inverse relationship for a given speed between the wavelength and frequency. All right, so for a constant given speed, frequency and the wavelength will be inversely related. All right, so the number of cycles per second, the best answer is going to be frequency, right? That's the definition. So D is the best answer for that one. All right, so for a given speed, wave speed, you know that the frequency of a wave is going to be inversely proportional to wavelength. Okay, C is the best answer for that one. All right, so here's a question for you. What determines the wave speed? All right, so we know it's going to be a product of the wavelength and the frequency, but the question is what determines it? Let's talk about sound waves, for example, right? How fast does a sound wave travel? Let me give you the answer for that one. It travels quite fast. It's about 773 miles per hour at room temperature. 773 miles per hour is the value. Give and take at room temperature, that's how fast it travels. In water, actually, it travels 4 times faster. In steel, it travels more than 17 times faster. Okay, so did I mention that it travels 4 times faster in water? And did I also mention that it travels more than 17 times faster in steel? So what does it mean? Which means that the wave speed depends on the medium within which it needs to travel. So what determines how fast the wave is going to travel is the medium itself. All right, so properties of the medium determines how fast the wave is going to travel. All right, so in water, it's going to travel faster, and steel is going to travel even faster. In water, it's 4 times faster, and steel is going to be more than 17 times faster. So the properties of the medium determines how fast the wave is going to travel. Speaking of the properties of the medium, what are the properties of a medium? What makes up the properties of a medium? Everything is made up of atoms and molecules. So obviously the density of the atoms and molecules will matter, right? Water is going to be denser than air, and steel is going to be denser than water. Okay, so does this mean that the denser the medium is, the faster it's going to go? Or is it just the opposite? Another thing that matters is how rigidly these molecules are attached to each other. In air, the molecules are not really attached, right? There's not much attachment. In water, you will have 2 molecules usually attached to each other, and they will roll over the other molecules. Right? So there's better amount of attachment, but that's the extent of it. In solid objects like steel, the molecules are rigidly attached. All right, so there are 2 factors that we have to consider: how rigid the connections are between the molecules. And notice that the stronger the connection between the molecules, the faster the disturbance is going to travel, right? Because if these molecules are strongly attached to each other, as soon as I vibrate one of them, if I move this one, the other one is going to move just as fast. Stronger the connection is, the larger the forces, the larger the acceleration is. That's what it means. So if I move this up and down, that vibration is going to travel real fast. So larger the molecular tension is, the faster it's going to move. How about the density of the molecules? Density of the molecules, think of the density of molecules in terms of the masses of these molecules. All right, so what does mass mean? Mass is just a measure of inertia, the measure of an object's tendency to retain its initial motion. It's related to, I don't know, it's related to the resistance to change in motion. Denser the material is, more massive it is, the more it's going to resist the change in motion. So more massive it is, the slower the wave is going to travel. That's what it means. So commonsensically, we could come up with 2 connections. Speed is going to be directly proportional to how rigid the attachments are, molecular tension. So T is going to represent molecular tension. And then it's going to be inversely proportional to the density of the material. All right, so the bigger the masses of the molecules or the atoms making up the material is, the slower it's going to travel. All right, so what determines how fast the wave is going to travel? So let's make it a summary statement now. It's going to be molecular tension. It's going to be directly related to molecular tension. So this is the Greek letter tau. And it's going to be inversely proportional to the molecular density. So we got the Greek letter M representing mass. All right, so the larger the molecular tension is, the faster it's going to move. The larger the density is, the slower it's going to move. So speed of the wave is going to depend on how rigid the connections between the molecules are. And it's going to be inversely proportional to the density. Larger the density is, the slower it's going to move, in essence. Okay, guys, we got a problem. The problem is this. Sound is going to travel 4 times faster than water. Water is going to be much denser than air. Okay, remember, when the density goes up, the wave is going to slow down. Steel is going to be much denser than water. If that understanding is correct, sound should be moving slowest in steel. The opposite is correct. All right, so the reason why that happens is as the density starts to go up, tension increases a lot more, proportionally a lot more. All right, As a result, the molecular tension is so great in steel that it's going to end up moving more than 17, the sound is going to end up traveling more than 17 times faster in steel than in air. All right, guys, speed of sound, speed of the sound wave, or any wave is going to be determined by the transmitting medium itself, right? It's the characteristics of the transmitting. So E is the best test for them. The medium itself determines how fast the wave is going to travel.
We're here in Ringing Rock Park in Bucks County, Pennsylvania. This is a very unique geological setting, and it's one of the few places in the world where rocks will ring when struck with a hammer.
For hundreds of years, people have been both mystified and amazed by these boulders that make music. Terry Beard is a musician who has been coming to the Ringing Rock Park since he was a boy.
I grew up in this area, and we used to drive by here a lot. And when I got my driver's license for the first time, I decided to take a ride one day and showed up in here and started banging on some rocks. Now, the first time I came back to the park, I was just here with no hammers. I didn't expect to be in here, actually. I kind of landed here by mistake. I was sitting there just banging with another rock. I realized, hey, there's music here. It was everywhere.
We asked Terry to show us some of the odd characteristics of the rocks. While most rocks will emit only a single pitch, like this boulder, some rocks contain two separate and distinct tones, perhaps caused by uneven internal stressing. More perplexing is the observation that rocks chipped from boulders ring at the same tone as their mother rock, despite their vast difference in size.
All right, that's interesting. All right, so a couple of things.
We're here in Ringing Rock Park in Bucks County, Pennsylvania.
Terry Beard is a musician who has been coming to the Ringing Rock Park since he was a boy.
I grew up in this area, and we used to drive by here a lot. And when I got my driver's license for the first
All right, so the question is,
I-
what's the difference between rocks that ring and the rocks that don't? What's the difference? I got news for you. They're identical. They got the same molecular structure. They will have the same molecular density,
decided to take a ride.
but they all have the same molecular tension.
These rocks are about 200 million years old. They date from the beginning of the Jurassic period, same Jurassic period as Jurassic Park, when T-Rex and his friends roamed the Earth.
Volcanic lava intruded into underground layers of rock in the area known as the Newark Basin. As it hardened under tremendous pressure, diabase rock was formed. Over time, the covering layers of earth and rock eroded. The diabase was uplifted and shattered into a field of boulders by glacial freezing and thawing.
There are many diabase outcrops in southeastern Pennsylvania, but ringing rocks are only found in boulder fields such as this one. And that's because the boulder fields are dry and hot and exposed to the sun, and the rocks weather differently than they do in areas that are wooded or shaded.
When diabase rock weathers, chemical erosion forms a mineral rind around the stones. This strong shell-like coating constricts the rocks and keeps them under constant pressure.
When the rock is under compression and you strike it with a hammer, it vibrates and it rings. If you strike an ordinary rock, it does not vibrate and it doesn't produce a sound. Hot and exposed to the...
All right, so what's the difference between these rocks? The ones that ring, the ringing rocks will have this chemical rind around them, right? All right, so this is a shell-like structure. So what it does, it causes compression within the structure of the rock, which means that it increases the tension among the molecules. So what happens when you increase the tension among the molecules? The disturbance is going to travel faster. That's what happens. But the question is this: the faster traveling disturbance, how does that increase the frequency? All right, because they're talking about pitch. Pitch is the same as frequency. How does the speed of the traveling wave, how does it coincide with the frequency of the vibration?
The stones. This strong shell-like coating constricts the rocks and keeps them under constant pressure.
When the rock is under compression and you strike it with a hammer, it vibrates and it rings. If you strike an ordinary rock, it does not vibrate and it doesn't produce a sound.
So compression increases the tension.
But if you
So larger the tension is, the faster the wave is traveling.
strike a rock that's under compression, such as these diabase boulders, they will vibrate. If you put your hand on the rock and hit it with a hammer, you can actually feel the rock vibrate. The same rock, if you remove the rind and they're no longer compressed, the same rock will no longer vibrate.
Well, this one over here
So the compression is the same as the tension.
is dead.
All right, so the larger the tension is, the faster the wave travels.
This one
So the question is the speed of the wave. How does it correlate with the frequency that you're
over
hearing?
here is alive.